So you want to encrypt. I tried to give a nice clickbait title to this. I started this talk with this grandiose idea that I was going to give you this overview and we were going to walk through a protocol and we were going to look at all the pitfalls and all the things that went wrong. And then I saw that we have 25 minutes and I realized that's not going to work. So we're going to do kind of an overview of this particular aspect and particular kind of encryption that doesn't actually show up very much, but is starting to, and a lot of things don't handle it. And so the problem is what is often called data at rest. This is the idea of the recipient and sender are known, but we don't have a two-way communication channel at the point. So there's something can be set up in advance, but then when the data is going through, it just goes from the sender to the recipient. Now that could be stored in some kind of storage. It could be forwarded, eventually get to somewhere. But you don't have an ACK that comes back or packets that go back and forth. Examples of these might be messages coming from IoT devices, that they are broadcasting these periodic. You set the device up at one point, but then these messages just go out through MQTT, for example, as published messages. You'd like them to be encrypted, authenticated, but you don't get a response back from the server because they're just kind of stored and processed later. Another big example is firmware images, where you want the firmware to be encrypted, you want the device to be able to decrypt it, but the protocol that transports the firmware doesn't know anything about all of that. So what we need, what our requirements are, these are kind of standard things. Authenticity, integrity, and privacy. I don't know how much time I have to go into detail. Authenticity, we want to know that who the message came from and that that's really for who it's from. Integrity, that the message has not been tampered with. And privacy, that someone who's not supposed to see the message doesn't see what's inside the message. So, just overview, what do we have as our tools? This is the kind of, if you go get a book on cryptography, this is the stuff you'll learn about. We'll be using 4 of these here, and I just want to go over these so we understand what they are. One of the most common things you'll run into is something known as a symmetric cipher. You probably hear of AES 128 or other numbers after that. And what this is given some message, M, this encrypts that message. It encodes the message such that a function D is able to decrypt that message and return the original message, but it has to have the same secret key that the sender of the message. Secret key is usually a fixed, something like 16 bytes, that kind of thing. You find this a lot. You see advertisements. We use AES 128 encryption, which is nice. That's good that they use a standard encryption, but it's only a tiny piece of the problem that you have to solve. So one other tool is a hash function. This would typically be something like SHA-256, hopefully not something like MD5, which is an old type of cipher, or old type of hash function that turns out doesn't actually have these properties. The real property here is we can take some arbitrary message M, we return a hash, which is a fixed size summary of that message, and with these properties include that if you have the hash, it reveals no information about the message, and nothing. Not the length, not the content, which has the other interesting property that any change to the message, 1 bit anywhere, results in a completely different hash. And there's a bunch of fun theoretical stuff to get into what that kind of implies and what you can gain from that, and the assumptions you can make if you know that's true, which we don't actually have proved, but it's kind of fun anyway. So 2 other things that we need to do this is something called key agreement. Maybe you've heard of something called Diffie-Hellman. Diffie-Hellman is an approach that was, well, it still is used, but it's a way of doing a key agreement. The idea is we have, it's getting a little mathy here, it's two parties, A and B, and each one of them has a private key and a public key. So this is run-of-the-mill public key cryptography. Given knowledge of each other's, so if they each know the other's public key and their own private key, they can agree on a secret between them, X, that cannot be determined by an entity that doesn't know at least one of the private keys. So an example of this would be something known as ECDH, if elliptic curve Diffie-Hellman math that we won't go into. But the idea is that for any two parties that want to communicate, this algorithm gives always the same key. And you can probably imagine that that's not ideal. So there's also something known as an ephemeral key exchange, where randomness is introduced into the process. And so the person generating one side has to create this kind of randomness that has to be sent to the other side, and it allows a unique key to be generated for each session. The caveat with this is that that's not authenticated. If the message containing that randomness is tampered with, you'll get two different keys, and well, you just probably won't be able to communicate. But you need to verify that. And then our last tool is something known as a digital signature. So the idea here is given same kind of thing, a public key and a private key, and we can take a message with the private key and generate a signature that someone else using the public key can validate that the message M is the message that was passed to the original signing function. And usually you don't sign a large message, you sign a hash, because these work over large numbers and are typically limited in the size of the numbers. So if you were around when RSA was really popular, there were a lot of things that were talked about of like never use the same key pair for signing and encryption. That advice was given. Turns out with modern RSA encodings, that's not even required. But it's perfectly fine to use the same key pair for both of these. We do it all the time for this, because the weaknesses were specific things with RSA that would reveal information about the keys. So that's our toolbox. We have symmetric ciphers. We can encode data. The problem with the symmetric cipher is it doesn't detect the message being tampered with. If something changes in the message, often something in the resulting message changes in the same bit changes. And so if you know the format of the data and that, there's a certain flag in this position, you can just set that in the encrypted, toggle that bit in the encrypted message, and it toggles it in the plain text. And so we need to make sure we use all of these to keep the message reliable. One other little additional thing, this is, I guess I will use the word becoming popular in the sense that there's some cryptographic properties. There's a question when you have authentication and you have encryption. And the question was always, well, do we authenticate the plain text and then encrypt it, or do we encrypt the message and authenticate the encrypted message? And it turns out there's advantages and disadvantages to both, and you can get into great debates about which is better. And it turns out even better than both is something called authenticated encryption, where at the same time you're encrypting the data, you compute this tag thing that you end up with at the end that authenticates the message as well. And because it's done at the same time in the same process, you don't have the same difficulties you have with this other thing. So for the most part, any kind of newly developed protocol is going to mandate that you use authenticated encryption. We've had some fun debates over this in the IETF. So we have these tools, but it still gives us a lot of choices. And then even when you make your choices, you still have more choices. It helps that there's standards. So authenticated encryption would typically be something like AES GCM 128. That's a specific algorithm using the AES cipher and this thing called a Galois counter that is passed through the data that when you first look at it, you can't imagine how that could be secure. And then turns out actually works really well and has some neat properties. SHA-256 is a hash function. Elliptic curve Diffie-Hellman ephemeral for the key exchange, and maybe DSA as the signature, easy DSA. And then we need to pick an elliptic curve. So that might be one commonly called P256, or depending on which entity, standards entity, will get some variant on the name for that. And then if you do Bitcoin, you have a different one that you use, and some complexity added to there. And then when you go to implement this, you'll have even more choices. And we have choices and choices and choices. The choices are not always good when you do this, because you can make ones that are unideal. But there's some trade-offs that we'll get into between deciding upon an encoding and then an implementation that's flexible enough so that that can be fixed if vulnerabilities are found later. So this is all nice. You got everything out of your cryptography book. We've got it. It turns out, though, there's still something missing from all of this. It's like most of these things result, so the cipher results in a blob of bytes, the symmetric cipher. Most of the key exchanges and other things result in a number. It's usually a big number that doesn't fit in one register on your processor, and you have to encode that some way. So to start with, we have to just encode these. But you also have to come up with how they're encoded and what data goes where, and when you compute a hash of something, which things are inside of that so that people get the same hash, what needs to be protected. And it turns out that this is, I won't say more important, because the actual underlying tools are really important for the security, but those are widely used, widely debated, tested. People will try to break them. And we have pretty good sense that they're probably reasonable until someone makes a working quantum computer, at least. But the protocols are really hard to do. And if you just look, the fact that we have TLS 1.0, 1.1, 1.2, 1.3, and they're different. That, you know, there's a few things in there that, well, let's make it more efficient, but there's a lot of stuff in there. It's like, well, we don't do that way anymore, because we discovered this about cryptography, and, well, we don't know if that's insecure, or we know that's insecure, so let's make sure we do it this way. So it turns out this is really hard, and, you know, these old ones are actually deprecated. You're not supposed to be using them for protocols. So the most important thing is, if you're going to be storing data, encrypting firmware, doing it, don't invent anything yourself, and I mean anything. If you think, well, you know, I'll just take these data and I'll just encode this in the message. You don't have people reviewing it. You don't have the whole of the internet trying to break it. And it's probably not going to be very secure, because this is really hard to get right. And it's very subtle where it can go wrong. So what do? Encrypted data at rest. You go read around. Nobody seems to do this. So there's a thing called COSI. And this is acronym city, the IETF. I guess that's an acronym in itself. Really likes these acronyms, and they like them to sound almost like words and stuff. So we have COSI, which is the CBOR object signing encryption, and I've got these RFC numbers here if you're interested in any of these. So CBOR, the concise binary object representation, you could think of that as a binary version of JSON. It's gaining in popularity. It's pretty easy to encode. It encodes, you know, integers, strings, basically integer, strings, arrays, and maps in a concise binary format. So that defines how a given data is represented. Then something like COSI says that you can encode, well, this kind of header is made up of a map, and this goes at the beginning, and this describes what an encryption looks like, this describes a signature, and that kind of thing. It gives you some specifics for that. And they're publicly defined. They go through the IETF, they come out as RFCs. There's a lot of scrutiny, and they're still really in infancy. These are just starting. And even then, most of COSI has been about signing messages. It was based on the what's called, well, Josie or Jose, I'm not sure. Take your pick on how to pronounce it. JOSE, which is the equivalent using JSON for the encoding. And it almost exclusively gets used for signing. It's not common to use it for encryption either. So encryption is young, which means it's also not getting as much scrutiny. But interestingly enough, the suit, which is another RFC in the IETF, has an encryption in process, which is built around COSI and CBOR. So it gets to start defining this. Is that what I have next? Yeah, so this gets us back to choices again. You know, now we've picked some more things and we have a lot more choices. COSI is useful, but it has numerous choices. It's kind of a data format. It's like, well, here's how you make headers, and here's some of the things that you can put in a header. Here's the two kinds of headers. They have protected headers and unprotected, and what do you put in there? And so you need to pick your algorithms, which we picked before. That's good. And you need to pick a profile. It's essentially what headers go in the messages that I'm using. So what this gives you is a balance between a generalized decoder that, you know, is able to understand the COSI spec and interpret messages, which you probably don't want in an embedded device. You know, something running on a microcontroller, you'd be using a lot of code for that. But if you are too specific and we say encode all of our algorithms and then a vulnerability is discovered in one of those, or the specifics of the protocol, if it's not flexible, then it won't be able to handle new messages that work around that. So, you know, what Suit is doing in this firmware encryption draft is they're specifying protocols, they're picking them and deciding. So it's a really good place to start even if you aren't doing firmware, to see what the choice is, because there's, again, many subtleties. When you do key agreement, you have to use a key derivation function, which has these parameters, and where do you get those, and what goes into them? And then you find some obscure research paper where if you didn't put this into the parameter, there's a vulnerability, and it can be used to do this. So I think the basic summary of that is, it's hard, and don't try to do it yourself. So if we do this, this does give us some confidence a little bit in the security. That, you know, I want to do an example. My device, I want to gather data from a sensor, and I want to sign in and encrypt it before I send it off so that it's insured. So if I grab this profile from the IETF, from the firmware encryption profile, and I'll just use that because I don't need to change it, and they've been thinking about this from a security. I think that we should be okay. The thing is, given the track record of other protocols, we're almost certainly going to find vulnerabilities. So the depressing conclusion of this is we can try, but we're still going to have to deal with things we learn and the possible vulnerabilities and weaknesses. So that's all I have for the slides. As I said at the beginning, I was kind of torn between this balance of how much do we overview and how much should we go into specifics. So we have a couple of minutes for some questions. If you have anything specific you want to ask, we can dive in. You could ask whatever you want, or we can talk about keys or whoever. So, and there's a microphone here if you want to pass that. There's also one there next to Etienne. Do you want to hand them?
Hello. So yeah, I would like to kind of negate your kind of whole conclusion or the statement of saying we shouldn't design our own protocols, and the kind of argument that you made that so what you were saying was basically the protocols that we design have less scrutiny as compared to TLS, which exists for several years. So that's kind of mean that we should do no innovation at all. So, so I would like to clarify this. That means we should never design any protocol in the future. So if you keep comparing with the history, which has been there for 30 years or even more, going back into the history, even into SSL where it all started, so that would mean we don't design any protocol at all, or so yeah.
Yes. Please. No, we should stop innovating and never do anything. No, that's not obviously what I'm saying here. Don't design a protocol in isolation, though. If you have a problem to solve, if you have something, and there's others that would be interested in that. So if you're just doing something and it works to use COSI, to use something that exists, use it. If it almost works, but doesn't meet some use case, join the working group mailing list. Get involved with that. If you have some completely different use case where this doesn't work, and you do need to come up with your own protocol, don't do it by yourself, because you'll probably get it wrong. Get involved. You know, you get with the other people, work through this, come up with it, because it turns out that it's a really long and arduous, painful process. I have my name on a couple of these RFCs, and the time it took for me to write the text that made it into the RFC is about 30 minutes. You know, I sat down and I wrote this. Then there's hours and hours and hours of working with people, debating, well, was that the right wording for this standard? Well, how does that impact this thing? And then somebody says, well, what about this research paper that shows this really weird, obscure way that, oh, that's actually not vulnerable, that's not secure, and we need to introduce something else in there. So, and again, it depends on what's the scope. If your data is just between two people and, you know, maybe it's, you know, there's always a cost of security, and you have to weigh that against the cost. And usually using something that exists is the cheapest way to move forward than to come up with a protocol. The thing you want to avoid is I'll just invent a protocol, this isn't hard, and then you do something simple, and there's all kinds of commercial products that do this. You know, you think of the really simple examples of like zip file encryption, or, you know, these tools that created as another industry of things to help you hack those, because they're actually not very secure. So does that kind of answer?
Yeah. I mean, just to conclude, like adding the word isolation completely answers the question. That's fine. So we should not design in isolation, working with the working group, coming up in a group, or working with that. That's perfectly fine.
Yeah.
Thanks.
You look in a cryptography book, and they'll tell you don't design your own cryptography. Don't go try to come up with a cipher. But that doesn't mean don't come. I mean, they hold contests to develop new ciphers. So it's not don't do it, it's just, it's really a lot of work and it's really hard. And the same kind of applies to protocols. That, yeah, they're not as deeply mathematical, maybe, but they're still all the same kind of subtleties that can result in vulnerabilities that one set of eyes isn't going to see. So, all right, anything else?
Hi, David.
Hi.
Question to the suit. As far as I understand, suit was about RFC, how to upgrade IoT devices on the field. And I haven't checked it in the recent years. So what you said, content was added, how to properly, I mean, defining similar protocols like a TLS, how to do the key agreement between the end device and upgrade service, and how to do data encryption rest on IoT devices. And all these are contained in a cozy envelope.
So yeah, so to clarify what I think you're asking, so SUIT is a group of RFCs. There's two core RFCs, which are an architecture and what's called a manifest format document, which describe the payload to hand firmware images from one device to another. There's a couple of others that are related, but then the one really related to this is the firmware encryption RFC, which is not finalized. It's still in draft, still being worked on. Actually, it's very soon to become a real RFC, but I don't believe it's been finalized yet. And that document describes, so we have COSI, it just references COSI. How do you use that in the context of a firmware image? What specific headers do you put in there? It gets very detailed as far as how you make a message. It has samples that you can test. They're like test vectors you can use against your code. And my suggestion from that is that problem is really close to a lot of other problems, that you have an encrypted piece of data that you want to store somewhere and a different recipient to receive it. It's probably good to at least start with that protocol to make sure you're doing the right, there's a lot of things that have been thought about. Does that kind of answer your question?
Yeah.
Okay.
So you can use that as an inspiration how to do.
Right. And I would say not even as much an inspiration as just do it, unless you have a strong reason to do something different. I mean, in my instance, I wanted to store an extra piece of data somewhere, and had a lot of debate with them as to where the right way, even the right place to put that was. You know, does it need to be an encrypted header? What tag should I be using? What problems will that cause with other people that see it? That kind of thing. Anything else? If not, thank you. Thank you for your attending.